Okay, so last time we were talking about expected value, and I did two examples with expected value. One had to do with this Pick 4 lottery, and the other one had to do with this insurance policy. So we talked about expected value. So these are all the concepts we looked at. We definitely talked about probability distributions. There were random variables, that column for random variables that was for discrete random variables, and then we had another column for probability. We talked about the requirements for a probability distribution. So the requirement is that if you add up that column of probabilities, it should equal 1. We calculated a mean and a variance. So actually, we calculated the mean and the standard deviation. We could take the standard deviation, square it to get the variance. And then we also talked about expected values. Okay, so today, and let's see, there's one more thing here. It says identifying unusual results. So that was still having to do with the mean and standard deviation. The reason we wanted the mean and the standard deviation when we were working with a probability distribution was because anything that is above the mean plus by 2 standard deviations and anything that is below the mean by 2 standard deviations would be considered unusual. So we would need to know what that mean and the standard deviation are in order to determine if something's unusual or not. Okay, so I have to change my symbols here. I keep writing an S, and it's supposed to be a sigma. Okay, let me try that one more time. There we go. All right, so in chapter 4, the symbols that we're seeing are mu and sigma. We're using these Greek letters for our measurements that come from our probability distribution. In chapter 2 and 3, we call that X bar and S. X bar and S. So this was when we were talking about chapter 2 and 3, but now we're in chapter 4, so our notation changes. So just be aware of that. So regardless, we're still looking at 2 standard deviations above the mean to be unusual and 2 standard deviations below the mean to be unusual. All right, so just keep in mind that our notation has changed when we're working with probability distributions. Okay, so today we are talking about the binomial probability distribution. So you already know the basics for probability distribution. So now we're going to talk about this one special distribution, and it's called the binomial probability distribution. So these binomial distributions are going to allow us to deal with circumstances in which only 2 outcomes are possible. But there's certain requirements. And so a binomial probability distribution results from a procedure that meets all of these requirements. So you have to have a fixed number of trials. That's your N. You have to have a fixed number of trials. The trials must be independent. The trials must be independent. So the outcome of any individual trial does not affect the probabilities in the other trials. Now, each trial must have all outcomes classified into 2 categories. So either you have a success or a failure. So you can only have 2 outcomes, success or failure. And the probability of a success is going to remain the same for all trials. The probability can't change. It's going to remain the same. So this is a special type of probability distribution. Again, it's called a binomial probability distribution. Okay, so we're going to go ahead and talk about some notation for this. All right, so when we write P of S, that's the probability of a success. So probability of a success is always known as P. And a probability of a failure is always known as Q. So P would be the probability of a success, and Q would be the probability of a failure. So if the probability of a success was 0.80, by this definition, what's the probability of a failure? Okay. So you see that definition, it's 1 minus P. Okay, good. So when you add up P and Q, it should equal 1. So 0.20 is correct. So if you're given the probability of a success, automatically you should know the probability of a failure because of this definition. Okay, good. All right. So here's some more notation. So N, again, is the number of fixed trials. X is the specific number of successes. So X is the specific number of successes in the N trials. X is going to be a whole number between 0 and N. So it's the specific number of successes you're getting in those N trials. P is the probability of a success. Q is the probability of a failure. And then P of X is the probability of getting exactly X successes among N trials. Now, X and P are referring to successes. So remember X, that's the specific number of successes. P is the probability of a success. So they refer to the same category. Whatever is described as success, that's what they're referring to. Okay, so one of the conditions when I was talking about the binomial probability distribution is that the trials must be independent. That was one of the conditions. The trials must be independent. Now, there is an exception that is made. When we are sampling without replacement, that means if you take a sample, you're not putting it back in when you obtain the next sample. So when you obtain a sample, you're not putting it back in before you obtain your next sample. You're leaving it out and then you're obtaining the next sample. So when sampling without replacement, you're going to consider events to be independent if your sample size is less than or equal to 5% of your population size. So if your sample size is just is less than or equal to 5% of your population size, it's okay if you're doing it without replacement. And the reason we say this is because without replacement, what happens is we don't have that independence anymore. The probability of the next is going to be affected by what happened before because it's without replacement. So you're changing your total value of N. But in this case, we are able to consider events to be independent if this rule applies. If your sample size is less than or equal to 5% of your population size. Okay, so this is where I hurried up last time and I was trying to tell you all the different methods there were for doing binomial probabilities. There are 3 methods. Let me just highlight that. There are 3 methods for finding the probabilities corresponding to the random variable x in a binomial distribution. I am going to show you all 3 methods, but one of them is the most efficient method. All right, so method number 1 is using the formula. So it's important for you to know why we use this formula. The next method would be using the tables that are in your book. And then the third method would be using your calculator. And what I hurried up to do last time is I wanted to show you this slide right here. These are all the strategies for finding binomial probabilities. Okay, so your first choice should always be to use your calculator. It's the most efficient method. I will show you the other methods, especially the formula, because you need to know why the formula works. And it's good to use it, a couple of times just to know how it works. But after that, you should be using your calculator. So the reason I go over the formula is to show you why it works. All right, so I kind of lost it. There it is. I lost the formula. All right, so this is the binomial probability formula. And it will allow you to find the probability if you have a binomial type problem. And of course, you have to make sure that these restrictions are met. You need to make sure that you're keeping this in mind, all of the requirements that we have. Okay, so the reason that I have this slide is so that you can see how we tie the past material to this one. So how does all this relate to everything we've already been talking about? So that's the reason for this. I'm trying to bring back some of the old stuff that we've been talking about so we can move on and connect the 2 topics. Okay, so here it says construct a probability distribution table for the number of girls born if a couple has 4 children. And X represents the number of girls born. So then the number of girls born, we have 0. Okay, so that 0 took on a new life there. It was supposed to be a pen and it turned out to be a highlighter. Let me try that again. Okay, there could be 1 girl, 2 girls, 3 girls, and 4 girls. I'm actually missing, I am missing a row here. So I'm going to fit it in there. So 3 girls and 4 girls. All right, so what I'm going to do is on the side here, let's see if I can fit it in on the side. Okay, so I'll do it right here. So I am going to go ahead and talk about the sample space. All right, so I'm going to go ahead and talk about, well, if we have 4 girls, we would have girl, 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 and there's also boy, boy, boy. So you'd have to go through the sample to find out what's in your sample space, so we can combine what we've been doing to where we're going. All right, so let me go ahead and write down that probability distribution. And I really have trouble with straight lines on this. Okay, so let me try this one. There is a tool here that has straight lines for me. Just takes, I have to go back and forth using that. Okay, so here's x and here's the probability of x. All right, so when x equals 0, there are no girls, so that means everyone's a boy. Okay, when x equals 1, that means we have 1 girl. So that can happen many ways. All right, that can happen many ways. So notice how I am taking that G and I'm moving it in a diagonal so that I consider all the ways where we have just one girl. So we have boy, girl, boy, boy. Then it's boy, boy, girl, boy. Then it's boy, 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 girl. Notice how that G went in the diagonal. That way I would consider all the possibilities where we have one girl. Okay? All right, so when we look at a probability, I'm going to go back and look at this, at the sample space. All right, when x equals 2, I'm considering all the possibilities where there's two girls. So G, G, B, B, that's one of them. And just because it's easier, I'm going to take those two G's and move them in a diagonal so I don't miss any of the possibilities. So I have B, and those two G's are just moving a little forward. So B, G, G, B, and then B, B, G, G. Now it can also be where there's, I was going to put two girls in the middle, but that I already have that one. Okay, so then the other one is G, B, B, G. I didn't have that one before. And then the opposite, B, G, G, B. I already have that one. Okay. So how do I know how many I'm supposed to have? Our counting rule told us how many we should expect. If we have 4 children, there's 2 possibilities for the first child, 2 possibilities for the second, 2 possibilities for the third, and 2 possibilities for the fourth. So our basic counting rule told us how many possibilities we should expect here. So here I'm expecting 16. All right, so I know to go back, and if I have them all, it should add up to 16. If I'm missing some, then I should see that as well. Okay, so now I have to consider all the possibilities where there are 3 girls. So if we have 3 girls, that means we only have 1 boy. So 1 boy, 3 girls. And so look at what I'm going to do with that. The B, it's going to go in a diagonal so that I don't miss them. So 3 girls, 1 boy. So those are all the ways I can arrange 3 girls and 1 boy. The last scenario is when we have all girls. And that was at the very beginning. We had all girls there. All right, so I'm hoping I have 16 of them. If not, then I missed something. All right, so I'm missing something, right? Because here I have 4, 4 here, and 4 here. That's 12. And then I have 2 here, so that I have 14. So I'm missing 2. So where I'm missing is down here, because that one didn't exactly have a pattern. So Nathan, you found that for us? Okay. So GB, GB, and then the other one, right? BG, the alternating ones, right? BG, BG. Good, thank you. Okay, so GB, GB, and BG, BG. I had to alternate them. So we need to know how many we're supposed to get. And finally, there's 16, so we know we shouldn't be looking for others. Okay, so this is the scenario where we have 2 girls. This is the scenario where we have 3 girls. And then over here, that's where we have 1 girl. All right, that's how many ways that can happen. Okay, now when we look at this, we talked about counting in section 4.6. Okay, we talked about counting and how many ways we can count when we have items that are identical. All right, so I'm just going to remind you about what we used when we counted items that were identical. So I'm going to try to count this without, if I didn't know the sample space, I'm going to try to count and see what I have there. So I have a total of 4, so 4 factorial would go up in the numerator. And then I have 3 that are identical. So 3 factorial would go in the denominator. So I only have to worry about the ones that are identical. The one that's not, it's just 1 factorial, so nothing really happens. So when you do 4 factorial divided by 3 factorial, we're supposed to get how many times we have 1 boy and 3 girls. So your n goes in the numerator, and then whatever is identical goes in the denominator. We have 3g, so that's why we have 3 factorial in the bottom. So when we have 4 factorial over 3 factorial, remember I've already showed you how to do a factorial on your calculator, and I'm sure we did some by hand. I don't know if I should open the calculator. But in this case, even if we did it by hand, 4 factorial is 4 times 3 times 2 times 1, and 3 factorial is 3 times 2 times 1. So you see what happens. So we have, there's 4 ways of arranging where we have 1 boy and 3 girls. There's four ways of making that happen. All right, so when we look at our formula, the one that I had here, this part of the formula, that does the counting for you. That's what I just did. This part does the counting for you. Now it's written a little differently, but that's all it's doing. It's that permutation where items are identical. Okay, so we know that's going to happen 4 times. So just like I've done it for this, I can do it for the others. So let me just do it for this one right here, one more. Okay, so we know we have 4 children. So that n goes in the numerator. The 4 factorial goes in the numerator. That's this part over here. X is the number of that's the successes, the number of successes. Here it's girls, so that's the 2 factorial. And then the n minus x, that's whatever's left over. So we have 2 items that are identical. We have 2 boys and 2 girls. So our denominator is 2 factorial, 2 factorial. So that tells us how many different counts, how many different ways there are of rearranging 2 girls and 2 boys. So again, that's 4 times 3 times 2 times 1. It seems easier to do this by hand than having to open the calculator. You might disagree on that, but it's just easier to see it this way. So we have 12 in the numerator and 2 in the denominator. So are there 6 ways here of arranging 2 boys and 2 girls? And so that's what that formula does. It allows us to count. Okay, so X, remember where we had B, B, G, G? So X is the number of successes, so there's 2. So here X was 2. And then N is 4, because there's 4 children. So this part where it says N minus X, that's just whatever remains. So N minus X would be the number of children minus the number of girls, gives you the number of boys. Okay. All right. So the whole reason for this is just to show you that the part of our formula here does the counting for us. And the reason that's important is so we don't have to keep doing the sample space. So we don't have to keep taking our time to look at all the different possibilities and draw out our sample space. So that's what it's supposed to be saving us. It's supposed to be saving us that time. Okay, so what I'm going to do is I am going to go ahead and put all the possibilities on here. We already had, this one was for 3 girls, so that happened 4 times. So I'm going to go ahead and put a 4 here. So I'm putting what the formula, the counting part of the formula gives us. All right, so I am writing down what the counting part of the formula gives us. So we had a 4 for when we have 3 girls, x equals 3 girls. And then we have a 6 for when x equals 2 girls. So there's a 6. So that's just counting how many ways that can happen. Okay, and just to continue using the counting rule for all girls would be, you could see that that only happens one time. But the counting rule is you take the number of children over how many items you have that are identical. So here we have 4. 4 factorial over 4 factorial, that's just a 1. So for all girls, you're going to get 1. That happens one time. That happens one time. All right, and then I have the last one here to do. 4 factorial, that's the number of children. And then how many do we have that are alike? That's 3 factorial. So we already know that 4 factorial divided by 3 factorial is 4. All right, and there it is, again, 4. Okay. So the question is there a way to do this problem without having to write the sample space? And there is. That's the formula that I was just pointing to. So what I'm doing right now is I'm showing you that the old way of doing it gives us the same as what the formula gives us. All right, so I'm going to just finish this here, and then I'm going to use the formula on the other side so you see how that works. All right, so when x equals 0, that only happens one time, so I'm going to put the 1 there. So the way that I filled this out was by looking at my sample space. How many ways does it happen? So I'm going to come back and compare it. Okay, so now I'm coming back to this page over here. Okay? All right, so like I said, this part does the counting for me. So I'm going to go ahead and fill out what I have, and then we're going to compare it to that other page. And we're only going to do this once. I'm not going to keep doing this over and over again. I'm just trying to show you how this works. Okay. So this is what I'm focusing on. So in this problem, n equals 4 because we have 4 children, and x equals, well, whatever it is on that column. So it changes from 0 to 1 to 2 to 3 to 4. So I'm just putting this in the formula. So I have n factorial, which is 4 factorial. So I'm just taking this and I'm plugging it in. Here, x is 0. So we have 4 minus 0 factorial, and dividing that by x factorial, which is 0 factorial. So by doing that, that gives you how many counts you have when you have 0 girls. So again, all I'm doing is putting everything in the formula. So now we have 4 factorial over n minus x, but x is 1 for this row. X is 1. So we have 4 minus 1 factorial. And that gets divided by x factorial, that's 1 factorial. All right, so I'm just doing the counting part of this. And I'm putting it into the formula. Okay, so now x is 2. So we have, the formula says 4 factorial over n minus x. N is 4. So that's 4 minus 2 factorial. And that's over x factorial, which is 2. So for each row, x keeps changing. N will always be 4. So you just have to keep plugging it into the part of the formula that does the counting for you. And that way, you don't have to keep writing out the sample space. Okay, so again, this is just the counting part. So 4 factorial over 4 factorial, that's just a 1. That's just 1. Over here, we have 4 factorial over 3 factorial. Now 1 factorial is just 1 I don't have to worry about. So 4 factorial over 3 factorial, that's just 4. And I had already done the calculation for that. And then this part right here, that's 4 factorial over 2 factorial times 2 factorial. So this is where we ended up getting 6. All right, so far I have 3 of them. I have 1, 4, and 6. Let's see what happened over here. I have 1, 4, and 6. All right, so if I continue, I am going to get the rest. All right, so I would have to continue. Again, the value of x changes depending on which row you're looking at, but n will always stay the same. So in order for you not to have to draw out that sample space, this is why the formula is important, because this part of the formula does accounting for you. That's the part of the formula that does accounting for you. So if I were to continue with that, I would continue finding all the different ways this can happen. When x equals 3, when x equals 4. It just tells us all the different ways that's going to happen. Okay? All right, so let me go ahead and finish my table here. So I've already counted that. And so what I'm going to do now is I'm looking at the formula, and I'm going to come up with the probability part. So let me change the color here of this pen. All right, so we already know that the first part is the counting part. This second part, that's the probability of a success, and x is how many successes you have. So P is the probability associated with x. So the probability of a girl, the probability of a success, the probability of having a girl is 0.5. So having a girl is 0.5. So then what we have now is the probability of a failure according to the definition for binomials. Q would be the probability of a failure. So Q is 1 minus P. So it's still 0.5. So girls is a success and boys would be considered the failure, because we have to assign x to be something, and in this case it's the number of girls, so x would be the success. All right, so I'm going to erase the factorial stuff because we've already done the calculation. All I really need is the number, the final number, which tells us how many ways this is going to happen. Okay, the rest takes into consideration how many successes we have, and it multiplies all those probabilities together. Okay, so for this one right here, we have one way that we can have 0 girls. That was already counted. The probability of a girl, that's 0.5. So we're going to multiply 0.5, and that's going to be to the power of x. So how many girls do we have here? We have 0 girls, so the exponent is 0. And then Q is 0.5. That's the probability of a failure. Well, here we don't have any girls. We have all boys. So that means 4 are boys, so 4 would go here. So the number in front does the counting for us. The P gives us a probability of a success. We have 0 girls, so that would be 0.5 to the 0. The next gives us the probability of a failure. That means how many boys we have. The probability of a boy is 0.5, and we have 4 of them. All right, so when you multiply all this together, you get the probability of having 0 girls in 4 children. And so it follows the formula that we have here. All right, so let me go ahead and clean this up. I'm just looking at the ways of counting. We only needed the final number there. All right, still cleaning it up. Okay, there it goes. So in this case, we had 4. 4 is how many ways we saw that we had 1 girl among 4 children. So the 4 counts how many ways that can happen. The probability of a girl is 0.5. Again, here we have 1 girl, so the exponent would be 1. Probability of a failure is 0.5, and if we have 1 girl, then that means we must have 3 boys. So the exponent on this is 3. And if you multiply all that out, that gives you the probability of having 1 girl among 4 children. And so hopefully you start seeing a pattern here. We just have to do a few more. If you still don't see the pattern, we still have to do a few more. Okay, try to clean that up as well. Okay. So for 2 girls, we know that that can happen 6 times. And so with 2 girls, we have the probability of getting a girl. We have 2 of them, so that's your exponent. The probability of not getting a girl is still 0.5. And that we have 2 boys. If we have 2 girls, we have 2 boys. So look at what's happening here. Your exponents will always add up to 4. So 0 girls and 4 boys for the first case. 1 girl and 3 boys for the second case. 2 girls and 2 boys. So your exponents will add up to your sample size, which is your n. And the 0.5 at the first 0.5, that's the probability of a success. Your second 0.5, that's the probability of a failure. Now in this example, P and Q just happen to be the same number, but that's not always going to be the case. All right, so without doing too much, with just following the pattern here, that's all I'm going to do now. I'm going to follow the pattern so I know that this is 0.5 and this is 0.5 for the next one. So notice that the exponents at the beginning, they were decreasing. So we had 0, 1, 2. So that must be a 3. Here we had 4, 3, 2. So they were increasing here, but decreasing here. Okay. So 0, 1, 2. So this must be a 3, and this must be a 1. Okay, and then the same thing for the bottom one. So now we have 4 girls and 0 boys. Now if we were to count, and we can get that from the other screen, you see how it happens where we have 1, 4, 6, and then it came back to 4, 1. So the 4, 1 repeat. All right, so we know that this happens 4 times and this happens 1 time. Okay, so now you get to multiply everything out. Who remembers what 0.5 to the 0 is? If your exponent is to the 0, what happens? Okay, you get 1, that's true. All right, so if you have an exponent to the 0, if you have an exponent of a 0, then you don't have to worry about that. That just is 1. Okay, so I'm just going to cross that out so you don't have to put it in your calculator. So this part is 1, and this part right here is 1. So we don't have to worry about putting that in our calculator. All right, so I'm just going to take you over. And you can do this by hand. You don't need the calculator, but it's just sometimes easier just to look at on this side. Okay, so for the first one, it happened one way, and there was 0.5, I think it was 0.5 to the 0. I'll still put it here just so that you see it. And then 0.5, we had all boys, so that was to the 4th. So notice what gives me an exponent here. It's this arrow that's right above the division key. That's my exponent. All right, so this is just 0.5 to the 4th. That's 1/2 to the 4th. 1/2 times 1/2 times 1/2 times 1/2. That's 1/16. So that's what I would expect to get here. 1/16, that 0.0625 is 1 out of 16. All right, so I'm going to go ahead and do second enter. That's just going to copy the previous line because I don't want to have to type that in all over again. So I'm just going to scroll over, and I think for the next line we had 3 boys, and we had 1 girl, and that happened, I'm just going to the left, that happened 4 times. Okay, so that's the probability of that happening. So I'm going to do a second enter because I don't want to have to type all that out again. Just track back with your arrow. The next situation, we had 2 boys and we had 2 girls. So you change that. And that we were able to see that happens 6 ways. Okay, so that part of the formula was able to count how many ways that happened. All right, so I'm going to go second enter, because I'm trying to get the one where it happens 4 ways again. So now we have 1 boy and 3 girls. Now it's 3 girls. Come on, 3 girls. There we go. And then that we saw happen 4 ways. So that's the probability there. And then finally the last one was where we had all girls. So I already did one of those where there was a 1 in front. There it is. But this time we had 4 girls. So that means there's 0 boys and 4 girls. Okay, and that just happened 1 time. So if you want to put it into your calculator, you can. You could also do it by hand because 0.5 is just 1/2 and you can multiply these fractions. And there's nothing, you could do that as well, as there's nothing wrong with that. So what I'm going to do is I'm going to go ahead and fill all these out. Now I showed you the decimal approximation. Here we could put the fraction. It doesn't matter. We could put both. Okay, so here I said I had 1/16, and that as a decimal was 0.0625. 0.0625. This next one, we have 4 over 1/2 to the 3rd, that's 1/8. So 1/2 times 1/2 times 1/2, that's our 1/8. But we already have another 1/2. So that ends up being 16 as well. All right, so I forgot the other 1/2. So that's our 16 because we have 3 1/2s here and another one here. Okay, and this is the one that ended up being 0.25. Okay, and then this one is 6 over 1/2 times 1/2 times 1/2 times 1/2. So this is our 0.375. And then again, this was 4/16, which is 0.25. And then 1/16, which is 0.0625. So by using this formula, we shouldn't have to bother with our sample space anymore because we already have something that does accounting for us. All right, so the first part of the formula does accounting for us. The second part of the formula counts looks at the probability of a success. The third part of the formula looks at the probability of a failure, and all that gets multiplied. All right, so if you add up the column, it's going to add up to 1. So the sum of all your probabilities in a probability distribution is going to equal 1. So it was very important to understand how this formula works. Notice that it comes right from our sample space. If we actually start counting them, you see it matches up. If we actually calculate the probability by just looking at our sample space, in this case, here, for example, if we saw the probability of a girl is 1/2 times 1/2 times 1/2 times 1/2, that gets us our answer. That's 1/16. That's what we ended up with over here, 1/16. So we can also get our probabilities just by looking at our sample space and multiplying the probabilities together. Okay, of course, if we do that for this one, if we multiply all our probabilities together, we get 1/2 times 1/2 times 1/2 times 1/2. It's still 1/16, but that happens 4 times. So 4 times 1 out of 16 is 4 out of 16 when we have 3 girls. And 4 out of 16 is what we got here. Okay, so this formula is supposed to make things easier, and we are supposed to able to calculate these probabilities faster than having to deal with a sample space. Okay, so that is the probability of, that's how we find the probability of a binomial. So from now on, we're just going to use the formula, somehow understanding that it does come from looking at our sample space and counting how many ways something can happen, and then calculating the probability by what we have in our sample space. So knowing that there is a connection from what we were doing in the previous chapter to what we're doing now, from now on we're just going to write down the probability, the formula for the probability for finding binomial probabilities. Okay, so this is what I had. It was probability of a success is n factorial over n minus x factorial times x factorial. That part does the counting for us. Then we're going to multiply that by the probability of a success. The exponent tells us how many successes we have. And then that gets multiplied by the probability of a failure, and the exponent tells us how many are left over. So n minus x. All right, so here a car insurance company has determined that 10% of all drivers were involved in a car accident last year. So this is the probability of being in a car accident. That's your P. That's the probability of a success, 0.10. So we're given that percentage, we turn it into a decimal. That represents our probability of a success. Among 12 drivers living on one particular street, 3 were involved in a car accident last year. So these 12 drivers, that's your N. Among 12 drivers living on one particular street, 3 of them were involved in a car accident. So the number of successes would be the number who were involved in a car accident, because P was the probability of getting into a car accident. X is the actual number from that sample who would get into a car accident. So that would be defined as your success. What is the probability of getting 3 who are involved in a car accident last year? Method 1 is using the formula. So you have your value for P, your value for N, and your value for X, and you plug that into your formula. So we have P of 3, N factorial, that's 12 factorial, over N minus X, so that's 12 minus 3 factorial. X is 3 factorial So this is the part of the formula that does the counting for you. So we don't have to rely on having to write up the sample space. P is the probability of a success, 0.10. How many successes we have here are 3, because 3 are getting into a car accident. So that's to the power 3. Okay, so what is Q? They didn't give us Q. Could we find Q if we needed to? Is there enough information to find Q? Any ideas? All right, so the formula was that Q is equal to 1 minus P. Good, yeah, so Q is 0.90. So you subtract 0.1 from 1 and you get 0.9. Okay, so let's go ahead and continue. So then 0.90 is what goes here. So if you have 3 successes and you had a sample size of 12, then you're left with 12 minus 3. You're left with 9 failures, and that's what's your exponent there. Now you could just put this in your calculator. I'd like to simplify this before we do that, before we put it in the calculator. 12 factorial over 12 minus 3, that's 9 factorial, times 3 factorial, and that's 0.1 to the 3rd power, and then 0.9 to the 9th power. Still, I think we can simplify this a little bit more before we actually put it on the calculator. Do you see 12 factorial over 9 factorial? So 12 factorial is 12 times 11 times 10 times 9, but I'm just going to put 9 factorial because that'll represent everything below 9. And then look what happens here. You have a 9 factorial in the denominator. So that 9 factorial and that 9 factorial, that can cancel. So really you just have 12 times 11 times 10 divided by 3 factorial. That's just an option. If you want to enter it in your calculator where it's a little bit simplified, you can do that. Otherwise, I mean, if you just want to enter it this way, that's okay too. All right, I thought simplifying it would make it nicer, but it didn't turn out to be that nice. So let me just enter it from here. Okay, so I'm going to just circle what I'm going to enter in my calculator. This right here is going to get entered. So I'm going to write that down because it disappears when I go to the calculator. So 12 factorial over 9 factorial times 3 factorial. All right, so let's see what happens. I'm going to clear what's already here. Okay, so I have 12 factorial. And so I have 12 factorial. You go to math, then to probability, and there's our factorial symbol, number 4. And I am going to divide that. In parentheses, you want to make sure you put whatever's in the denominator, keep it together. So I put it in parentheses to keep it together. So that's 9 factorial. So 9, go to math, go to probability, and it's option number 4, times 3 factorial. Go to math, go to probability, and number 4 is factorial. All right, so that's what's going to count how many ways this can happen. So I'm going to press enter, and that's 220 ways. Wow, 220. Okay, so now you take 220 and then multiply it by the probability of a success. So 0.1, and we have 3 successes. And that's going to get multiplied by the probability of a failure, which was 0.9, and that's to the 9th power. Now, when I say 0.10, that's the same thing as 0.1. So if I had just put 0.1 there, that would have been the same thing. I'm just going to try to keep it the way that I wrote it. So 0.1 is the same thing as 0.10, and 0.9 is the same thing as 0.90. Okay? All right, so that's it. That's what I'm going to go ahead and press enter, and that should be my answer. All right, so that is the probability of getting 3 successes among your 12. So what you do is you verify first. Of course, I didn't do it, but you want to verify that this is a binomial type problem. So you go through the requirements. There are only 2 outcomes here. Either you're involved in a car accident or you're not involved in a car accident. You have a fixed number of trials. That was our 12. So when you go through those requirements, you see that this does follow what we have there. So this was equal to 120, this part right here. And so when we put it all in the calculator, it ended up being 0.0852. Okay, so here's the thing in Chapter 5, which is not consistent to what we've already been doing in Chapter 4. Remember, probabilities were always rounded to 3 significant digits. Chapter 4, we kept talking about how probabilities were rounded to 3 significant digits. But when you're doing the homework, they actually give you rules as to how to round. They just actually they don't give you rules. They give you instructions as to how to round. So for this one, they round to 3 places. Not 3 significant digits, but they end up rounding to 3 places. So just keep that in mind. Make sure you read the rounding instructions before you enter your answer. Probabilities are supposed to get rounded to 3 significant digits, but when you're doing the homework, that changes. All right, so for this one, I would say it's 0.852. That's rounding it to 3 significant digits. Okay, so that's how you use the formula. You're going to have a P, which is the probability of a success. You have to find the probability of a failure. You just subtract from 1. And then you have to have a sample size. That's your fixed number of trials, your N, and you have to know what X is. You just plug it all in the formula and you get the probability of that happening. Okay, so no more having to deal with sample spaces. This part of our formula counts for us. Okay, so it's nice to have a formula, but even using the formula, it's a lot of work, right? It's a lot of work. Okay, so here's method 2. Method 2 is using the appendix you have in the back of your book. Now I'm going to have to change this because what I realized is that they cut the tables and it only goes up to 8. Your sample size only goes up to 8. So here I'm going to have to change that to 8 drivers. I'm going to have to change that to 8 drivers. Okay, that's supposed to be an arrow. There we go. So I'm changing that to 8 drivers. So instead of 12, we're changing that to 8. Again, that's because the table in your book doesn't have that. So I'm going to do the following. I'm going to go ahead and open up, show you where to get these tables. So let me move you over to my stat lab. Go where it says, where you have the ebook. So here it says chapter contents on the left side. So I'm going to click on that. And then this is where you're going to there's a formula card for the midterm. You want to make sure that you print this out. It's right here. Right now I'm just going to go ahead and look at, I don't know if it's here. I'll go ahead and check it. It's usually not there, but I don't see another option for it. So what the tables have is it's already calculated those probabilities for us. All right, so I'm searching for it. That's not what we need. Oh, wait a minute. Maybe that's, nope, not yet. Okay, so as I suspected, it's not on that table. But look at the side here. It has Appendix A, and that's, I'm going to check there. And there it is. Okay, so when you do try to open the tables, you'll see a table of contents to the left. And that table of contents has Appendix A. Right, so that's what we have. These are our tables. These are our binomial probabilities. So it's already been calculated for us. We're just going to go ahead and use the tables here. So we don't have to use the formula if you're using method 2. Okay, now the only problem is that these tables only go to 8. The publisher did not provide anything after 8. I'm sure you can find it online, but it's not in your book. It just goes to 8. Okay, so that's what I'm using. All right, so look at the top here. It has the N. So let's see, I'm going to take a copy of this and move it over. Okay, let's see if I can make that a little bigger. No, it's not any better. Okay. Okay, and then I'm going to take a snapshot of that. And we have it on our screen. I might have to come back to it, but I'll point to it on the whiteboard. Okay, so for this one, we have a car insurance company has determined that 10% of all drivers are involved in a car accident. So again, P is 0.10. We have to find Q just like we did before. So the problem really hasn't changed other than the fact that I had to change N. N is 8. And here it says, what is the probability of getting at most 3? So we have to interpret what that means. At most 3. So in the previous question, X was equal to 3. But here it says at most 3. What is the probability of getting at most 3 who were involved in a car accident last year? So again, it's a binomial type problem because either you're involved in a car accident or you're not. So at most 3, the most you can have is 3. Anything below is also part of it. At most 3. So that means 3, 2, 1, and 0. So you're finding the probabilities for when X equals 0, 1, 2, and 3. If I had to use the formula for this, I would have to use the formula 4 times. Once for when X is 0, once for, then again for 1, then again for 2, then again for 3. Then I would take all those answers and add them together. And that's a lot of work. All right, so that's why we have these tables. Okay, so let's see how the table works. We have to find out when P is 0.10 and when N is 8. All right, so you see that P is at the top. Okay, so P is up here. So 0.10, that is the third column. Okay, so P is at the top here. Those are your probabilities. So 0.10 is at the top, and then N is over here. Now this one only goes to 6, so I have to go to the next one. So remember, we're on the third column. That's what we were looking at. We're in the third column. Okay, so that's still not 8. All right, so let me go back. It didn't copy it. All right, so here it is again. So we're in the third column. All right, so this is the column that we need to pay attention to. That's the third column because the probability was 0.1 there. This first column, that's your N. So N equals 8 right there. All right, so the next thing I need to pay attention is to the values of X. So remember I said x was equal to 0, 1, 2, and 3. These are the values of x, and you match that all up. So n equals 8 here, and then these are the values for x. Those are your x's. So x is 0, 1, 2, 3. So you match it up with its probabilities, and there you have the probabilities already. There they are. So you just add up all those probabilities. That's what we're adding up. Okay, so what I'm going to do in the previous page right here, it's going to be the probability of 0 plus the probability of 1 and 2 and 3. So I'm just going to copy what the table has. So for 0, it has 0.430. For 1, it's 0.383. For 2, it's 0.149. And for 3, it's 0.033. So again, you're just looking at the table, and all I did was I copied down these probabilities right there. So notice that the tables, they rounded it to 3 places. So why did they not round it to 3 significant digits? It's because there's not enough space. You see on some of the probabilities they just put 0. It's not really 0, but it was something really close to 0. But there's only so much space on the table. So that was what I consider one of the reasons that they're rounding binomial probabilities to 3 places, because of the way the tables were printed out. Okay, so all I did was I just copied those, and now we have them there without having to use the formula. That's the probability of 0, 1, 2, and 3. So you just add all those together, and what do you get? All right, so you all agree on the same thing? Good, okay. So, and that's it. We did this without having to use the binomial formula. Now, the disadvantage with the table, as you can see, is that when you're working from the table, you're stuck with these probabilities up here. And you could only use the ones that are here. So what if your probability was 0.33? Well, 0.33 is not here, 0.3 is there, but 0.33 is not there. So you are stuck with whatever's on the table. Okay, so that has some limitations. And then of course, if you're looking at the book, it only goes to 8. So we can't use another value of n other than 8. You can't go beyond 8. So obviously we have some limitations with the table. But you can get the complete tables online. All right. So easier than the formula, but still not very efficient. Okay, so finally we're on this part where it says using technology. So I am going to solve this problem using technology. And then I'm going to go back to all of the other examples. Actually, I'm redoing them here, as you see. I'm going to redo all the other examples using technology. Okay, so I'm going to redo the examples first because you've already seen them. All right, so I'm going to skip to where it says I'm going to redo the examples. This is the very first one we got, and then I'm going to compare our answer to what we got with the formula. So this is back when we used the formula. All right, so again, nothing's changed because P is still 0.10. Q was derived to be 0.90. That hasn't changed. N is 12 for this one. N equals 12. That's what I was trying to write. And it says, what is the probability of getting 3? So X is equal to 3. All right, so on your calculator, you are going to go to a key that, let me go ahead, and I was trying to write it here first and it didn't work out. But on your calculator, you're going to go to second var. So I'm going to write it on here first, and then I'll take you to the calculator. So you're going to type in the second key and then the vars key. For when you have one value of x, you're going to use the binomial PDF. So if you just have one value of x, you're going to use the binomial PDF. And the way you enter it is you have to enter the n, comma, p, comma, x in that order. So the PDF is when you have one value for x. All right, so keeping that in mind, I'm going to go ahead and move you to the calculator. All right, so I'm going to clear what I had here. Clear everything. Okay, so I said we're going to go to second vars. So second vars, then you should look for binomial PDF. You have to be careful because there are other types of PDFs on here. And we are only interested right now in the binomial PDF. So don't get sidetracked by all the other PDFs. You have to scroll down until you see binomial PDF. And there it is. There's two options. There's the binomial PDF and the binomial CDF. When you have one value of x, you're using the binomial PDF. Okay, so I'm going to select that. All right, so when I wrote it on the whiteboard, that is if you have the older version of the TI-84, you have to enter your information horizontally. So it's the n, comma, p, comma, x. On the newer calculator, that's what I have. The trials, you're entering everything vertically. So the trials, that's our n, so that's 12. Using your arrow key, you just come back down. P is 0.10, and then x, the one value of x we had was 3. So on the newer version, which is what I have, your information is entered from top to bottom. But on the old TI-84, your information is entered from left to right. So you have to enter 12, comma, 0.10, comma, 3, and then close your parentheses. All right, so here I'm going to go over the word paste and press enter. And see, what you see on the screen here is what you have to actually type in on the old version of the TI-84. You'll see binomial PDF, and you actually have to type in those numbers. If you press enter, that is your probability, and that's what we ended up getting with the formula. I'm going to go back and check it, make sure it was. So 0.0852. All right, so on the older calculator, you're going to see this. Binomial PDF 12, comma, 0.10, comma, 3, and that's going to give you 0.0852. I'm rounding it to 3 significant digits. Keep in mind now when you do the homework, it's going to ask you for 3 places after the decimal. Unless they've changed it from the last time that I was looking at the homework. But just beware that you have to read the instructions when you're doing the homework of how do you round. Okay, so I'm just going to take you back to when we used the formula. And so remember 0.0852, keep that number in mind. So I'm going to click and go back and take you to that slide. And there it is. So you can compare the two methods. Method 1, I used the formula. Method 3, I used the calculator. So which was more efficient? So on the midterm, you can definitely use your calculator. It will save you time. But I do require that you write down exactly what you typed in to the calculator. So what I'm writing down here, what I'm boxing, you need to tell me what command you used and what you entered. So binomial PDF and then what you entered. So you have to make sure you write that out. Okay? All right, so the PDF command, the binomial PDF, is used when you have one value of x. So let's go ahead and redo another example. And the other one I'm redoing is example 8. This is the one that I used the table on. So I had to change my 12. Remember, because the table doesn't go to 12, I could have ended up getting one online, but I'm sticking with what's in your book, and that's not on there. Okay, so I changed it to 8. So n is equal to 8, and p was equal to 0.10. Now x, it said at most 3. So at most 3 refers to how many successes you have. So x is equal to at most 3. The most it can be is 3. So 0, 1, and 2 are okay. Anything but nothing greater than 3. At most 3. All right, so when you're trying to find the binomial probability and you're given more than one value of x, as is the case here, you're going to go to second vars, and you are going to select the binomial CDF. So the binomial CDF is if you have more than one value of x. All right, and the way you enter your information is going to be n, comma, p, comma, the largest value of x. So the largest value that x can be. So what it does is it calculates the value here when x is 3 and then everything that comes before 3. So when you put a 3 in for x, it's going to calculate when x is 3, 2, 1, and 0. All right, so just keep in mind what our values are here. N is 8, so you have to enter n, p, and then the largest value x can be. Okay, so let's go back to the calculator. All right, so now I'm looking for the binomial CDF. So you're going to go to second vars, and there are a few other CDFs on there. So you need to make sure you're looking at the right one. It's the binomial CDF. So scroll down, or you could scroll up. If you scroll up, look what happens. You get to the very bottom of the list. So you can scroll up or scroll down. Eventually, you'll see it. Again, there are other CDFs. Make sure you are looking at the binomial CDF. So I'm going to press enter. And again, in the newer TI-84, the information goes from top to bottom. So we have n, which I believe was 8. That's the one I had changed. P is 0.10. And then x, the largest x value that we could have is 3. So when you put a 3 in here, it calculates 3, 2, 1, and 0. Yeah, if you have another type of calculator that's not a TI-84, then you must have a manual for how to do it. Yeah, so this is on the 84. Okay, and if you have the 83, it's the same thing. Okay, so here it is, n, p, and x, but I use the binomial CDF. I use the binomial CDF. All right, so that I'm going to go back and write down 0.99. I'm going to do it to 3 places now. 0.995. We'll round it to 0.995. All right, so the next example, we're going to deal with the at least 3 situation. So if you had that wording, at least, we're going to go ahead and go over that example next. This one was for the at most. And when I say at most, that means it could be worded in a couple of different ways. But if the wording is such where the values of x that you're looking are below, instead of above, it's always going to be just the binomial CDF. So if you have more than one value of x, and you want to calculate the value of x that are below a certain number, including that number, then it's going to be the CDF. But that least situation is a little different. All right, so we'll do that one next. All right, so let me just finish this one. So binomial CDF, and I entered 8, comma p, comma x, which is the largest value x can be here. And I got 0.995. I'm just curious, is that what we ended up getting with the table? All right, that's our table, right? Okay, so we can use our calculator instead of our table. All right, so it's the same thing. Now I'm just rounding it to 3 places because obviously the table had rounded them to 3 places. Okay, so the last one I want to do is the at least situation. Okay, so I'm going to go back to that problem that I skipped that has at least 3. And at the end, I'm going to summarize all that for you. So there's 3 scenarios where you have exactly one value of x at most or at least. So there's 3 scenarios we're looking at. Okay, so method 3 is the calculator. Nothing has changed here. N, well, I went back to 12 now. N is 12. P is 0.10. Now, x, it says at least 3. So the least you can have is 3. The least you can have is 3. So if I list 3 here, where do I stop? The least you can have is 3. Where do I stop? Where do you think? Yeah, because we only had 12, right? So you have to go all the way to 12. Okay, so at least 3, the least you can have is 3. Now I'm going to write the ones we don't want. And I'll put that in a different color. I do not want 0. I do not want 1 or 2. Those are the ones I do not want. So at least 3 means you're going to take 3 and above. Those are the probabilities we want. However, you just saw how that binomial CDF works. You just saw how that binomial CDF works. Here it is again. The binomial CDF, when you put in that value of x, it calculates that value and everything that comes to the left. Not to the right, but everything that comes to the left. That's how that CDF command works. So if you have that at least situation where you want all the numbers to the right instead of all the numbers to the left, you have to make an adjustment. All right, so that's where I was. So if I use the binomial CDF, and I do that because I have more than one value of x. So n is 12, p is 0.1. Now the value of x that I enter here, it's going to find that value of x and everything to the left. But look, I don't want everything to the left. I want everything to the right. So let's try finding the probability of what we don't want first. Let's find the probabilities of what we don't want, and we'll use that to find the probability of what we do want. So to find the probability of what we don't want, what do I enter in place of x? Okay, yes, 2. All right, so when you enter 2, it's going to calculate 2 and everything to the left. 2 and everything to the left. And those are the probabilities we do not want. And that's how the CDF works. Whatever value of x you enter, it calculates that value and everything to the left. Okay, well, there's something very important you know about probabilities. You know that when you add up your probabilities in a probability distribution, it's always going to equal 1. So if that's the case, what we're going to do is we're going to take the probability of what we don't want and subtract it from 1 to get the probability of what we do want. So when you have the at least 3 situation, it's going to be 1 minus binomial CDF. And the value of what you put here is always going to be 1 less than what is written. So we put 2. 2 is 1 less from 3, right? 2 is smaller than 3 by 1. So that's always the case. If it says at least, it's always going to be 1 minus the binomial CDF. And the value of x that you type in is going to be 1 smaller than what you're given. So 2 is 1 smaller than 3. All right, so Samantha, you already got our answer for that. All right, so let me just go ahead and quickly, let's verify that for others who couldn't get that. All right, I just forgot what it was that I had on there and I just deleted it, but let's see if I could remember. It was 1 minus binomial CDF, so that was second bars. Binomial CDF, I'm going to go up instead of down because it seems like that gets me there faster. Binomial CDF, there it is. Then I'm going to press enter. Remember, this goes from top to bottom, so I believe n was 12, p was 0.1, and we said for x we're going to enter 2. So remember, before this it was 1 minus. So I'm going to press enter. Okay, so I got something different. So let me check, make sure I entered everything. 1 minus binomial CDF. N was 12, so I'm going to do second enter just to see what I entered. N, P, and X. Yeah, it looks good. Okay, so we are going to round to 3 places because that's what the new rule is for Chapter 5. The probabilities for Chapter 5. We end up rounding to 3 places because our tables have 3 places. Now, make sure you read the instructions on the homework, though, before you do that. Okay, so 0.11 is what we would say. 3 places would be 0.11. Okay? All right, 0.11. So don't forget about the 1 in front. So I gave you a scenario for when you're finding binomial probabilities when x is equal to 1 value, then when x is equal to more than 1 value that are located to the left, and then when they're located to the right. All right, so I want to emphasize that when you're solving binomial probabilities, your first choice should be to use the calculator. It will save you time. If you're going to be using the formula, you're not going to have enough time on the exam. When you're using the calculator, everything that I wrote here, that's your work. So what did you do? I did 1 minus binomial CDF, and I have N, P, and X listed in there, so you know exactly what I typed in. Okay. So that would be your first choice. That's the most efficient way of solving binomial problems. And So you might wonder, why did I spend so much time on that formula? It's important for you to know that there's a connection between what we did in Chapter 4 and what we're doing in Chapter 5. And that formula comes from our counting rules in Chapter 4, so that it allows us to count how many arrangements are possible so that we can determine what our probabilities are. So you understand the formula. I would use it a few times, and but then after that, on your homework, just make sure you know how to use the calculator. All right, so let's see how much more. So again, I just said, okay, this part of the formula counts how many ways things can happen. And then probability of a success, and then the other was probability of a failure. Okay, so what I'm going to do here is I'm just going to give you a quick summary of what we did on the calculator. So sometimes this is the wording, exactly. But it doesn't always have to be exactly. If you have one value of x, if it's understood that you only have one value of x, then you should use the binomial PDF. All right. If you have more than one value of x, and if you have the at most situation, then it's going to be it's going to be binomial CDF. That's the CDF. And what you're entering is going to be n comma p comma x. And x is the largest value that x can be. All right, so for the more than one x, there are two scenarios where you have the at most and when you have the at least. And for the at least, it's going to be 1 minus the binomial CDF. And it's n comma p, comma, now the x that you put here is 1 lower than what they're saying. Okay, so the value of x is going to be 1 lower than what's given. Remember to put that 1 lower. So those are the 3 ways you're going to be using your calculator. And of course, I gave you the, let's see if I can highlight these. There we go. So I gave you the wording, but it doesn't have to be the word exactly. I mean, anything where you know you're only looking at one value of x. And here I put at most, but it doesn't have to be that specific wording. It's just any time you're looking at the values of x that are to the left. So if your values of x are located to the left, then that's the at most situation. All right, so that would be the at most. If your values of x are located to the left. And then the at least situation is any wording that you take your values of x that are located to the right. All right, so any wording that sets it up that way. Okay. So hopefully that calculator simplifies things, but there's still rules within it, so you still have to understand those rules. Okay, then the last thing that we're looking at is finding the mean and the standard deviation for a binomial distribution. The nice thing about this is that the formulas for binomial distributions for the binomial probability distributions are much easier than the ones for the regular probability distributions. So these are the ones we had already talked about. The formula for my standard deviation seemed to not appear here. There it is. So these are the formulas we had already talked about. So if we were just looking at any discrete probability distribution, we would use the formulas we talked about. But for the binomial distribution, we have special formulas. And the nice thing about them is that they're much easier to use. So the mean is just n times p. The variance is n times p times q. And the standard deviation is n times p times q, but it's the square root of that. So these formulas are only for binomial type problems. So here's my last example. I think it's my last example. Yes, it is. And so we have a company that manufactures batteries in batches of 10, so that must be my n. We have a 3% rate of defect. So here our probability is 0.03. That's the probability of a success. A success here would be that the batteries, the probability that the battery is defective. The probability of getting a defective batch. All right, so P is 0.03, N is 10. And we have enough information to find the mean and the standard deviation. Because according to the rule, the mean is n times p, and the standard deviation is the square root of n times p times q. Okay, so we have n and p. I don't see q. So was there a way for us to find q when it's not given? All right, so 0.97. Okay, good. So it's 1 minus p. All right, so knowing that, let's go ahead and do that calculation really quick. So for the mean, it's just n times p, so that's 10 times 0.03. And then for the standard deviation, it's the square root of n times p times q. So for the mean, you're just multiplying 10 times 0.03, which is just 0.3, right? So the mean is 0.3. And for the standard deviation, we're just taking the square root of that. So the square root of, what do you get for the square root of that? So here we're going to just round it to the 10th place. I didn't tell you how to round, so round it to the 10th place. So Samantha, you got 0.535. Okay, so if I round it to the 10th place, I'm assuming it's 0.5. Yes? Good. Okay. So nice thing about the binomial distribution is that the mean, calculating the mean and the standard deviation, the mean, the standard deviation, and the variance, the formulas are much easier to work with. If you wanted to use the older formulas, then you would have to create a table. But it's much more work to do it that way. So these formulas, again, just work for binomial type problems. Only for binomial type problems. Okay, I thought I was almost done, but I just saw there's one more slide. Okay, so this is just, I think I've already talked about this. This is just a reminder that the way we find maximum and usual values is the same as we've done in chapters 2 and 3. In chapters 2 and 3, we called it the mean minus 2 standard deviations and the mean plus 2 standard deviations. So the notation was different. But anything above the mean by 2 standard deviations was unusual. And so in this chapter, the notation is different. So I talked about this already, I remember, because I made the same mistake. I was going to put a plus there, and I meant to do a minus. All right, so it's the mean plus 2 standard deviations. So the mean minus 2 standard deviations is still the minimum usual value, and the mean plus 2 standard deviations is the maximum usual value. Anything that falls beyond are unusual, or considered to be unusual events. Okay, and I think I put that at the very end because I thought I would forget it. But that's it. Okay, we are done with Chapter 5. So I'm just going to print out the participants list because I just like to know who's attending live. Okay, so let me show you before you log out. Let me just show you what I have on my stat lab. Okay, so a reminder that when you go to homework, you have to go to homework, and under homework, I already have your Chapter 5 homework on there, so you should be working on that already. The way that you get points for watching this lecture, of course, is by clicking on lecture number 9, which is under your homework. So if you click on lecture number 9, which is under homework, you'll start seeing the questions that I was asking you. And you only have 2 questions, but each question has 2 parts to it. So that's what we were talking about, okay? So it's not very long. So if you want to finish it first and then log out, it's up to you. If you have any questions, let me know. All right, so that's it for today. So I'll stop the recording, but I will stay logged on. Those of you who are attending live, if you have any questions, you can ask. This does not go for those of you who are watching the recording, but those of you who are here live, I will stay logged on if you have questions. All right, so I just found a mistake on the questions that I asked for you to complete. So I'm just going to go ahead and do that problem instead of changing it, because I just realized if I change it, then that might create more problems. So I am going to show you, go back to the homework. And so if you go to homework and you look at lecture number 9, and click on it, and then it's question number 2. Let's do this question together. All right, so it's this last one. It says, for the following binomial problem, where p is 0.10, n is 10, x is at least 4, which means that x is 4, 5, 6, 7, 8, 9, or 10, which is the correct entry on your calculator? So this is the at least situation, so I should have had 1 minus on these. But not considering the 1 minus, which one do you think is the correct option here? All right, so yes, it's because you go 1 lower, so it is B. So it's the binomial CDF. That's the only one that would make sense. We wouldn't use the PDF. We wouldn't put a 4 in there because it's the at least situation. So B would be the only one that would work. All right, so I have to do the next one. All right, so for this one, it says there are 3 methods for solving binomial probabilities. The most efficient method is, so what is the answer to that one? All right, so that one we had already talked about, right? Use your calculator. All right, so I had to do that one in order to check my answer. So that's what's going to get you the right answer. So even if you look at this, I mean, you have to select something. And so the only one that will work is the binomial CDF, where you enter a 3. A 3 is 1 less than 4. Nothing else would work. Nothing else falls under that. But you would actually do 1 minus binomial CDF. And I forgot the 1 minus on all of them. But that's the one that comes the closest to it. All right? So just make a note that that's what you're choosing. And that'll be easier than me having to go back and fix it. Okay, so that's it.